uploaded a 20-hour YouTube video because I did not finish recording after class yesterday.
You didn't cut it?
No, I didn't cut it. So
Let me sit through it?
no, so it's got my 6th hour and then like 14 hours of just dead space just in here. And then yeah, you can, and you can do it on YouTube too, which is what I'm gonna do. Yeah. All right, so 4.2.5, what is an integral really? And this is where we're going to start trying to think about integrals a little bit differently, because up to this point, we have thought about integrals as areas under curves. And that is a very useful way to think about integrals, because they are, in fact, the areas under curves. In fact, that's where all the calculations come from. We break up those areas into tiny rectangles. We add up all those rectangles, and we get the area under a curve. However, that's not what an integral actually measures. So today we're going to look at a lot of other useful applications for integrals that you will definitely see on your College Board AP test. Because if you think about it, area under the curve, not that useful on its own. However, as we started off this class with, the first problem we did in question 1.1, we made the connection between the area under the curve of velocity and the distance that a car had traveled. And that's exactly what we're going to look at today. So, for example, 492. The key word today, by the way, is accumulation. That's what I wanted to highlight there. Integrals as accumulators, which is how we're going to think about integrals from now on. We're going to think about an integral as an accumulation function. You can still think about it as an area function, by the way, because area is just the accumulation of several tiny rectangles. And as they accumulate, they add an area. I love the word accumulation. I'm not really sure why. It just flows nicely. Plus, it makes me think of snow and winter time and snow days, and that's my favorite part. So, you know what? This week and last week have been full of close calls. I have not had fun commutes to work the last few days. No. And 72, I got a thing I gotta say on the record too while I'm recording. 72 has this thing where, like, and I guess people do this everywhere. Like, we're all cruising around, it's 4 or 5 cars in a row. We're all going 40, 45. We're all just enjoying ourselves, getting to work on time or safely. And then here's some guy in the back, big truck, big tires. I'm going to pass everybody. Snow on my windshield, snow. I'm like, what are you doing? And guess what happens? The passing lane ends, and he merges right back in. Like, you didn't get anywhere. Buddy, I'll see you when we get to the first stoplight in Kalkaska. I'll see you there, too, because you'll be right there at the same time. Every day, to and from. We end up at the same stoplight in Acme and the first stoplight in Kalkaska every day. I end up with the same person.
Just get a plunger, man, and just...
I know. I just want to, I want to wave and it was like, pull up, hi. Okay, anyway. Okay, 492. Cars, speaking of cars, a car is traveling along a straight road with a velocity given by some function v of t. All that matters is that the integral from 3 to 7 of that velocity is equal to 120. So, according to the context of this problem, what does the value 120 represent? What are its units, and explain how you know. I'm going to show you a really key thing. It's a funny acronym. It's going to make me chuckle. Jeff's going to chuckle too. NUT is the acronym. And that stands for noun, unit, and time. And the good thing, it's a good thing because you guys are a little...
Always gonna remember for the
Yep,
exam.
you'll always remember that. Noun, unit, time. Because I can guarantee there will be a question like this on the free response section of your College Board test, which a human being is going to read. And they're going to be looking for you to understand specific things about a... oh, God, I know, huh? I'm digging myself a hole.
Blame Hayden.
Yeah. So what we want to interpret out of this thing, the noun in this case is the miles. Because when you look at velocity is represented in, is there a unit on this one? Miles per hour. Perfect. When you take the integral of a rate, what you're going to do is you're going to pay attention to the noun in miles per hour. And the noun is going to be miles. Basically, when you take the integral, you just kind of throw the per hour part away. Because when you accumulate all of those velocities over time 3 to 7, you're just going to get the miles that have been traveled. And that's exactly what's going on here. So this means we have gone 120 miles. That's the noun part. Actually, it's the noun and the unit. 120 miles. Let's see. As far as the time goes, we've traveled 120 miles from t equals 3 to t equals 7. From t equals 3 to t equals 7. Now, you might replace this part of the phrase with something more specific depending on the problem. Sometimes they'll say that the integrals, maybe you say that noon is 0. So now 3 would be 3 o'clock p.m. and 7 would be 7 o'clock p.m. Or they'll say that, oh, 0 is 8 o'clock a.m., so 3 would be 11 o'clock a.m., and 7 would be 3 o'clock p.m. It doesn't matter. You might replace that with something more specific, but that's exactly what this integral means. It means that you've traveled 120 miles because you're integrating the velocity, which means you're going back up a level to distance. In question B, you have somebody claiming that 120 is the area under VT, and so the unit should be square units, and that's a misconception. Yes, we can measure an integral by using area, but that does not mean that an integral is always in terms of area. This represents 120 miles on this problem. That's the key. So this is question B is all about what's going on. When we started this lesson, we talked about how the difference between the area under a curve versus an accumulation function. You can represent the accumulation of miles with an area, but that's not actually an area. So even though area is a useful way to think about integrals, it's not actually an area. So it wouldn't be like miles squared. That would be silly. 120 miles. Let's take a look at some more examples here to help you get this idea of NUT out. So question A, 493A, has 3 different integrals. And for each one, we're going to write a complete sentence that will describe what's going on. We're going to do this together, one by one. Here we go. Question I, you have the integral from 0 to 75 of P of C dc. P is the represents the rate that a coffee shop makes a profit in dollars per ounces of coffee sold C. So what this is measuring is you have 125.93. We have $125.93 were made. That would be the first part of this. As far as the time, now time is not actually the variable here. It's dollars per ounces. So that would be how much money they made on the first 75 ounces of coffee. There's a lot of variability you can have here with these sentences that you're going to write, but they're basically looking for you to understand that the integral of that rate function, P of t is given to you as a rate. That's the key word. It's the rate the coffee shop makes money in dollars per ounces. When you take the integral, you basically throw the per ounces part away, and now you're going back up a level to just dollars. It's the same idea as a position function relates to a velocity function. In this case, instead of velocity, it's dollars per ounces. So position would just be dollars. That's exactly what's going on. Question 2, you have the integral from 150 to 2,000. H is going to represent the rate at which a bee produces honey in teaspoons per round trips. Yikes. This means that these guys, 150 and 2,000, those are the number of round trips that this bee has made. And yes, these kind of questions do show up on your AP test, and they are always bizarre. They're usually subject for memes later on, too. Which you're not supposed to post because you're not supposed to talk on the internet about your score. But anyway. So H is the rate at which a bee produces honey in teaspoons per round trip. So when we do this integral, we're basically going to throw away the per round trip part. So this means that 13 teaspoons of honey were produced again, there you got your noun, you got your number, and you got your unit. Maybe N stands for number instead of noun. That might be a better idea. You got your number, you got your unit, and now all you got to think about is time. But time is weird in this case because it's actually the number of round trips they've made. I might say from round trips 150 through 2,000. Again, these sentences are very formulaic and wordy, but they are following exactly what the integral is saying. The bee made 13 teaspoons of honey from round trips 150 through 2,000. You'll see the round trips over on the integral. And question 3. This is an interesting one here too. See that absolute value? That's going to change our answer a little bit. This is very similar to the question that we did up above. Very similar. Because it's the integral from 3 to 7 of velocity. It's the velocity of a car traveling on a north-south highway in miles per hour. There's your thing right there. So these are going to be hours, the 3 and the 7. And our integral, 360, is going to be in miles. Right there. Oh, look, see, it's exactly what I said. T of 0 is 8 o'clock a.m. So 3 in this case would be 11 o'clock a.m. And 7 would be 3 o'clock p.m. Time is always weird. Time is one of the weirdest things we measure, I think. We should get rid of it. Time is just a social construct anyway, right? So now here's the other part of this. See that absolute value of v of t? That's going to change. We're going to have to add just a careful word into our answer. This means that we don't care if the car was traveling forward or backward. All we care is that it was traveling. So 360 total miles were traveled, I guess is probably what I want to say there. So 360 total miles. Oops, I don't know how to spell. I gotta need to move over here. 360 total miles were traveled from, let's think about this carefully here. If 0 is 8 o'clock, then 3 is 11 o'clock a.m. And then 7 would be 3 o'clock p.m. Of course, that's just an American thing, too. The rest of the world uses a military time, which makes way more sense. Why do we do this? Things America does that I don't understand.
We're just not.
Why is it that at noon we just roll the clock back to 0 again?
The island of
is we do use it. It's just depends
I know.
on what job and stuff. You
Yep.
the island of Summeroy in Norway is trying to get rid of time.
I believe that. Norway?
Yep.
I mean, it's all dark up there right now.
Oh yeah.
It's all. That's the craziest part. When I went to Iceland this summer, it was the summer solstice and it got dark. It was day all the time.
300
It was. And right now, it's night. It's just night all the time. And they won't see daylight again until like March. Yeah, they just have dark up there.
Norwegian island was built first time freezing.
Yeah, right?
all day.
Yeah. You know, it's really bizarre. One more story about time in the cherry industry where I work. Since we work through the night, we keep track of processing days. So our day starts at 6 o'clock a.m. And then we work until we call it 30 o'clock. Because at 24, that's when the day changes. Like technically now it's the new day because it's midnight and you're at the new day. But for these 6 hours here, this 6 hours of production time still counts as production time because it's still the same shift that started the previous day. So even though, let's say that you're processing cherries, I don't know, let's say it's 2 in the morning on July 13th, that still counts as July 12th's production because we started the shift then. So we would say 2 in the morning would be 26 o'clock of the 12th.
So it's just
Time
12,
is-
It's just 12-hour shifts.
Yeah, we do 2 12-hour shifts.
Yeah.
Yep.
That's kind of.
Even you?
Nah, I'm kind of a weird. I work the day shift, you might say, but I'm there before the day shift starts, and I'm there a little bit after day shift finishes. So I work 13, 14 hours. But I have a lot more chill of a job. I'm not like on the line or anything. I'm just on the phone. Okay, anyway. So question B, what do all these integrals have in common? What I want you to see right now is what the integration symbol does to the integrand. I don't know if we've talked about these vocabulary terms before. The integrand is the thing inside of the integral. And basically what we're doing here is we're throwing away the per part of the units. When you take the integral of a rate, what's important about what all these things have in common is that they are all a rate, something per something. Dollars per ounces, teaspoons per round trips, miles per hour. And when you take the integral, you throw away the rate part and you just go back up one level to the accumulation part. It stops being miles per hour and starts just being miles. Instead of dollars per ounces, it's just dollars, like that. You're basically adding up all those little rates that are happening over time and getting back to just how much you're actually accumulating there. And that's that. So question C is really what we're talking about here. Antiderivatives are often called accumulation functions because they compute net change of the integrand over a given interval. We should talk about that really quick. If you have an integral from a to b of some function, let's just call it f of x. We really haven't talked about this vocabulary yet. This part is what's called the integrand. And b to a, b minus a, would be the interval. What's going to happen here is when you compute that net change, what you're actually going to be doing is computing displacement, which is the net change of a function. Remember that displacement doesn't take into account where you started. It just tells you how much you changed. A lot of times these problems are going to come with some sort of initial condition. They're going to say that, oh, there already was 6 feet of snow on the ground, and then it started snowing at this rate. So you have to remember to add that original amount on. The integral just tells you what the change was. From now on, we're going to be thinking about integrals as accumulators. They're going to be agents of change. How much stuff has been added to a situation, or in some cases, subtracted, because integrals can be negative also. With this in mind, let's talk about what accumulates in each one of these examples. Very easy question. What's accumulating? In question 1, dollars are accumulating. Very simple. The dollars are accumulating. Every ounce of coffee you sell, you're accumulating a little bit of dollars there. In number 2, it's honey. Teaspoons of honey specifically, but that's it. And in question 3, you're accumulating miles. It's a very calculus thing to do, to start thinking about if you looked at the speedometer of your car at 60 separate instances for 1 minute, you could theoretically figure out how far the car traveled by adding up those little times. With that in mind, there are 3 big questions that I want to investigate, and to investigate them, I'm going to break you into 3 teams to investigate them. We have 494, 495, and 496. Each one of them is a little different. I'm going to break you into teams randomly, kind of like yesterday. And what's going to happen is at the end of, let's say, 20 minutes, I'm going to have each team kind of get up and describe their discoveries about each question in a public speaking setting, which means you have to be, I know, that's not too bad. You'll be fine. Public speaking, valuables.
You are just illiterate.
It was literally this.
You know my ideal class schedule?
What?
Yeah, I'd rather trade all my Algebra 1 classes for public speaking classes and keep this class.
It's this. It was this.
We had a speech class in high school. And I feel like it was required.
What?
We had a speech class and you had to give speeches. I took it my senior year and I remember really liking it.
Well, wouldn't that be like a debate class then?
Yeah, like
so
debate.
They would mix
It was
up-
the debate team, the coach, debate team coach, legendary Elk Rapids educator by the name of Terry Reisig.
That's a cool last name.
She has a cool last name.
He sounds like a folk hero.
She was like the reason Elk Rapids was kind of put on the map as an education. It was her and Mrs. O. She was like they had a powerhouse program there. Not sure if they still do. Okay, let's have we lost Lucas.
How would
So we're
you
at team 2.
Yeah, so we lost Lucas completely.
Let's have Abby, Violet, and Tyler be working on 494. Luis.
Yeah, exactly.
Sorry,
Let's
dude.
have Vivian, Kara,
Man,
and
girl,
Hayden
child.
work on 495, and that means that Sydney and Jeff work on 496.
Yeah,
There was a graphing calculator for this, my friend. There is some rough work to be done in these problems. All these problems are going to be challenging, so to prepare, the first 2 problems are going to be pretty easy. First parts, then it gets a little bit. You're going to want to graph. None of the functions are nice functions either. That's the thing you should get used to. For your
Okay,
debate
I
test.
love
But you're going to do it all in the calculator, so don't worry about it.
We don't need it? Want calculator. I'm still using it. Want calculator. I'm still using it. We got the one.
If you're watching this video after the fact, go ahead and skip ahead 20 minutes because we're going to do the presentations after that.
Daniel A. Dinosaur.
It's super weird. This is, I mean... initial mass of the meteor.
This one should change.
Subtract. We want this to be greater than it's more than 50 kilograms, the world is destroyed. Can't have that.
It's so slow.
Oh yeah, it takes forever to graph. So, oh, I can throw it there. This is what mine looked like when I got it. Oh, hang on. Oh, that's for these guys. Yeah, that's for this problem. Yeah, these guys over here. Well, I put the scale that I use is from 0 to 20,000. So I knew that 10,000 would be right in the middle of that, so I just kind of eyeballed it. It took my calculator about 5 minutes to graph this red line. It happens somewhere in his 50s. That's the book the answer that the book provides is in his 50s, which I was like, come on. Now, as far as you guys go, Sydney and Jeff, let's see, yeah. Oh, it's gonna be. Is there steam coming off of it yet? E to the x over 20 power. We haven't done anything with E yet. There's a lot of stuff we got to do still. So that's what the change in mass will be. Yeah, I think that's right. I think you guys are correct. Yep. Sorry, Danny the dinosaur. Let's talk. I want to talk to you guys back here too. Let's see. So you guys, 495 team back there, you want to remember the key idea here is if you have an initial amount plus the integral, that's going to tell you kind of where you are now. So what you guys need to do first of all is figure out what the original radius of that sucker was. And you're going to do that by solving that the volume of 2400 is equal to 4/3 pi r cubed, since that's the volume of the sphere. So yeah, the volume of the Lollipop was 2400 cubic centimeters. And volume formula for that would be 4/3 pi radius cubed. So you're going to need to work backwards and solve what the actual original radius was. No, it's actually just solving an algebra problem. I would multiply by 3/4, then I would divide by pi, and then I would take the cube root. It's like 8.2 or something. Just to give you help. Logarithms. Which part? D? Yeah, but 10,000 doesn't equal E because this is the rate. Well, the problem is that you don't have the original function. You have the rate function. So if you wanted to have a function for the actual number of hairs, I mean, the best thing you have for that would be the integral from 0 to x of r of t dt. This actually tells you the actual physical number of gray hairs he has, which is what you want to solve. This is what equals 10,000. The rate is how fast he's gaining those hairs. It's not the number of hairs he has. Those are two different ideas. If you look at the original graph of r of t, you can see it's increasing. He's gaining more gray hairs more quickly, but the actual number of hairs would be when you took the derivative of that, or evaluate the integral. Like that. That's what you want to find is equal to 10,000. So I suppose what you might want to do is, if you could, find a general antiderivative for that function, which I don't know how to do. If you could find a function whose integral or whose derivative is that, then you could use that and plug in 21 or plug in 10,000 or whatever. Yeah. You will pretty soon here be taking the derivative of functions like that. It's very easy. No, the easiest derivative formula. You can memorize it right now. You want to know it? If the original function is e to the x, the derivative is e to the x. Yeah, that's a really popular meme fuel too. The e to the x is the function that's the derivative of itself. That's a popular one. Let's see. I'm giving these guys a little more time to think about. I'm going to list all the derivative formulas you guys are expected to know for this class. If you have f of x times g of x, that's a product rule. That's f prime times original g plus g prime times original f. Product rule, quotient rule is a pain, not fun. F of x divided by g of x is equal to original g times f prime minus original f times g prime all over g of x squared. Quotient rule. We all mentioned e to the x already. You get your trig ones. Sine is cosine. Cosine is negative sine. Tangent is secant squared. Cosecant is negative cosecant x cotangent x. Those are all your trig derivatives. That might be it. Oh, natural log. Oh, yeah. Oh, this is like... We still have 4 chapters left in this class. We're about halfway through. The derivative of natural log is 1 over x. That's a 1 and 2. Which one? That's a natural log. That's an ln natural log. Yeah. The general logarithm is no longer on the AP test, so you don't need to worry about it. It's not hard though, but I think that might be it for general derivatives. But then antiderivatives, there's like 20,000 of them. There's a whole bunch. These are all the derivative functions that you're going to be responsible for this year. I mean, we have lots of time to talk about these. What I like about this, the pace of this curriculum, is that if I was doing this year what I'm doing last year, we wouldn't be talking about integrals for another 3 months. So instead of getting bogged down and memorizing all these formulas, basically we've done one of them. We've done power rule. And we're using that as a way to discuss kind of the ideas behind derivatives and integration and the relationship between them. And then in the back half, we'll start introducing all these formulas, which you can then apply to situations that you already kind of understand. So I like that approach. Which one? Tangent, the derivative of tangent is secant squared. Yeah, I was writing it very hastily. The most memorizing ones are the trig derivatives. They're not fun at all. I guess doing back over there with the... Okay. Just over it? Okay. Can we talk about some answers? Jeff and Sydney, you guys want to go first?
No.
You guys got an easy one.
Okay, so meteor is gonna hit, right? And it's like 199 kilometers. Or, I mean mass. Sorry, kilograms.
Yeah.
And we gotta figure out if it's gonna make them die or not. Because if it's bigger than 50 kilograms, they're gonna all these dinosaurs in that train, they're all gonna die. So we figured it out, and they're gonna die.
Oh, rats.
Yeah.
So yeah, in this problem, if the mass of there's a meteorite hurtling towards Earth, if the mass is more than 50 kilograms, all the dinosaurs will be destroyed. This problem, all three of these problems revolve around kind of the same idea. I don't know about your guys' so much. Well, your guys' does, but it's kind of hidden. And it's the idea that an integral on its own is not enough to tell you a certain position. You need to know an initial condition also. So the formula that's going on here, I'm kind of right off to the side. I wrote it on the board over there. You kind of have to have an initial position plus your integral. Because the integral will tell you the displacement, how much change there's been. But that isn't really useful unless you kind of know where things started. So in this case, they did tell us, if you're looking carefully, if you haven't looked at this problem before, let's give it a quick read over. You have a function here, k of m, which will tell you the rate at which the mass decreases. M is measured in kilometers. So it appears here that the weight of the meteorite is a function of its distance from Earth, which is kind of a weird way to think about weight. Usually we think about weight relating to time, but in this case the weight or the mass actually relates back to how far it is from Earth. Kind of weird, but that's the case. At the moment that Daniel the dinosaur spots the meteor, it's 100 kilometers from Earth, and its mass is 199 kilograms. I don't know how he knows that, but we couldn't do the problem otherwise. So the integral that you want to evaluate is the integral from 0 to 100 of the given function. Another thing that all three of these problems have in common is that the functions are bonkers. Like, they're not the kind of thing you would ever be expected to deal with by hand ever. This is the difference between the calculator and non-calculator section of the AP test. On the calculator section, they'll give you these ridiculous functions that nobody's ever expected to take the derivative by hand. You're just going to let the calculator do it, because the calculator can do derivatives and integrals pretty quick, more or less. Anyway, so here's what happens. You take the original 199 kilometers, you work out the integral, and you realize that over the next 100 kilometers, it's going to be losing 147.4 whatever kilograms of mass. However, when you do the subtraction, it's not enough. Sorry, Danny the dinosaur, it's all gone. 51.587 kilograms. So, unfortunately, the dinosaurs will not survive. Let's talk about the hair problem. 494. Luis's hair started going gray when he was a young child. On his 17th birthday, he counts 70 strands of white hair. So that's probably the closest thing you guys get to an initial condition here, is that you know that when he's 17, he has 70 strands of hair. You also there's actually two. You also know that when he's born, he has 0 strands of white hair. That's kind of the one you want to use, though. I did this problem, and I think you guys did too, without using the 1770 at all. You don't actually need it. Of course, his mother, who is insane, keeps data on these kind of things and has a rate function for the rate at which he's gaining white hairs or gray hairs right there. Yeah. Yeah, me too. I'm getting a little salt and pepper in my 30s here. What's important about all three of these questions is the function they give you is a rate. It's not an accumulation. It's just a rate at which things are happening. You have to use an integral to actually find the number of what's going on there. So I will ask you guys, were you able to find out how many gray hairs he had on his 21st birthday?
79.
How many?
100, well, do you want the decimal?
Yeah, I'll have the decimal.
127.97.
I kind of got that too, I think, 127.97. This is just the integral from 0 to 21 of that rate function. The reason why you guys don't need to worry about an initial condition is because your initial condition is 0. Let's assume he had 0 gray hairs on his 0th birthday. So from 0 to 21, you can just evaluate that. That'll tell you how many gray hairs he has. Question D is kind of bonkers. It's going to kind of show you guys the process to go through it. Question D is asking if the human head has 10,000 hairs, then how long will it be till he actually has all white hair if he doesn't go bald first? So to do this, you can actually use the calculator. I'll just show you guys kind of what I did here. I'll make calculator cam pretty big too for the purpose of the video later. So on the graphing calculator, this is a thing that we'll practice with future questions for everybody too, because it's a thing you probably will be required to do at some point. So the original function goes there in y1. That's your e to the 0.14x. And here you have the accumulation function. Notice that the variable is there at the top bound of this integral there, 0 to x of y1. I just went ahead and I could have typed that again because it's not too long, but a shortcut is just to use y1 there. And then I also graphed the line 10,000 because I want to know when this line crosses 10,000. And then I graphed it. It took my calculator about 5 minutes to make this line because it has to do a lot of thinking to make these points that are in red here appear. But you can see red is the actual numbers of gray hairs that he has. Blue is just the rate at which he's gaining those gray hairs. So the red is up here, and you can see it crosses 10,000 right about there. It's about 51 something. When he's 51 years old, he gains, or he has all white hair, something like that. And then, 95. I didn't get to the end of this problem before the end of lunch. I was working on it a little bit before you guys got here, though. I'll be curious to see what you guys came up with. Did you guys find the actual radius of the lollipop at the beginning of the event?
Yeah, but
It's okay. I think I had it on this calculator right here. I think by far you guys, you had the hardest problem. The lollipop problem is kind of weird. But we can look at it all together. Why don't we? So you got this lollipop. You're entering your lollipop eating competition. The original volume is 24,000 centimeters cubed, and the first contestant to lick their way to the center is the winner. You've been practicing for months, and have found that as you lick away to the center, the rate of the radius changes, which kind of makes sense. As the candy goes away, it's going to start getting smaller faster, which again is a really big kind of aha in calculus, is that things don't change the same way over time. Think about the classic example is a Gatorade jug, like a big 5-gallon Gatorade jug on a table. If you flip it open, it drains really fast at first. But what happens is as the molecules of water leave the tub, there's less of them pressing down, and so the rate at which the water is leaving the tank is actually getting smaller over time. So that's where calculus really has its power, because it can take into account all of those changing values. And that's why this kind of math really has a lot of weight to it. Anyway, so what's going on in this problem, the first thing you got to do is figure out the initial radius of the lollipop by doing a little bit of an algebra problem. You got to know what the volume formula for a sphere is and then solve it backwards. I did this by multiplying by 3 over 4. I'm just going to use the calculator really quick. I have it on my right here. I did this by taking 2400 and multiplying by 3/4, and then dividing by pi, and then taking the cube root. And it looks like it's about 8.3 centimeters or so initially. So that was kind of the initial radius of this problem. Next, in question B, they kind of ask you to evaluate the integral from 0 to 10. And since this is measured, this rate here is measured in centimeters per minute, which is really key to this problem. The integral from 0 to 10 would be the amount of centimeters of the lollipop that have been decayed away by your tongue or whatever in the first 10 minutes. It's surprisingly small. If you do that integral, it's only like 0.299 or something. So in this case, what you end up with is you have about 8.3 for the initial radius plus the change, which is about negative 0.2399. So the radius of the lollipop at 10 minutes is still about 8.0657 centimeters, which is still a pretty big lollipop if you think about it. This is at 10 centimeters, though. The last question is, last year the winner took exactly 50 minutes to finish it. Do you have a good chance of beating last year's record? Well, we can do that exact same kind of math here, because we know the lollipop was originally about 8.305 centimeters. So let's add on the integral from 0 to 50 of your function that you have in this problem, which is a bizarre function in this case, too. It's negative 3 over 2500 t times the natural log of 9t. Hey, natural log showing up for the first time in this calc class. So we can throw this in the calculator really quick and see the answer. It's not even that tough to do. This is, by the way, a thing you will definitely be required to do at some point, is to do some sort of weird integral expression kind of like this. 8.305, whoops, plus the integral from 0 to 50. Oh my God, here we go. Okay, negative fraction, 3 over 2500 x. Oops, got to go back in here. close parentheses, times the natural log of 9x, close parentheses, dx. There you go. That will do it. We're looking for a oh, look at that. That means the lollipop will be gone in 50 minutes. So you will beat the record because the lollipop will be gone. If it was a positive number, there would still be some radius left. But since it's negative, you're done. So yes, because you got a negative answer here, that means you'll get it.
What if it hits 0? Does that mean it
That means you'd tie. If it was 0, you'd be tied. Exactly correct. Exactly tied. I think that's all I really wanted to talk about really quick. Not really interested. 497 is a good problem. Maybe for us to talk about tomorrow a little bit. Maybe before the quiz tomorrow, we'll look at 497 maybe as a warm-up. That might be a good one to save. It's going to be a team quiz anyway. It won't even be that long. It'll be fine. It'll be great. And tomorrow you'll have a night off of homework too. And then Thursday and Friday, presumably that plan A happens and I actually do have my gallbladder out. You'll have circuit trainings those days too with my dad. You'll ask him about the Forest area basketball game. It's a good story. He has a lot of good stories from his reffing days. The homework is all of the sections here, 498 all the way through. It's not too bad. The video is already posted, 98 through 105. Now that you have integrals if you look at 105, for example, it says that the key sentence here is recall that a Riemann sum does not have to be a sigma notation. You can use integrals from now on. Way easier.
And I